Okay. Let us finish what we have done last time. We introduced the, the different features of the crystal structures. We are going to talk today about the three most common crystal structures, which are the BCC crystal structure, the FCC crystal structures, and the HCP crystal structures. But in addition to that, we are also going to deal with the simple cubic crystal structure. For illustration, actually, it helps the student understand the crystal structure better when we start with the simple one. So to start with, we are going to look at the simple. Let me make this larger. We are going to start with the simple cubic crystal structure. In the simple cubic crystal structure, we have, as we have already mentioned, we have atoms at the corners of a cube. And this is how the crystal structure looks like. It's a simple cubic. So simple for the term that it is very simple, and cubic means that it is a cube basically, and the atoms get the positions there. These are the lattice positions of the atoms which we are showing here, and this is the these are the atoms actually in the lattice positions that you could see there. So each atom is in the corner of the cube, as you could see there. So the first thing that we want to determine here is the coordination number. How do we calculate the coordination number? The coordination number is calculated. Why do we need the coordination number? Actually, when it comes to identifying the type of crystal structure the material has, normally it is determined by the coordination number. They look at what is the coordination number. From that number, you know what type of crystal structure we are having. So, what is the coordination number? It's the number of nearest neighbors or touching atoms to a specific atom. So we basically go to one of the atoms, any of the atoms, let's say this atom, and see how many atoms are touching this atom in this crystal structure. So from here, you can know, I mean, this is one unit cell. Of course, there are neighboring unit cells there as well, and there is one neighboring unit cell at the top, and there is one neighboring unit cell in the front of this as well. So this atom is basically touching how many atoms? It's touching this atom in this direction, and it's touching this atom, as you could see, it's touching here, it's touching this atom in this direction, and it's touching this atom in this direction as well. This is where it is touching. But in addition to that, Nan?
6.
Yes, exactly. But we did not say yes. We said this is 1, this is 2, this is 3. There is one atom here, of course, it is touching. Why? Because there is a unit cell here, and there is a unit cell on the top of this unit cell. Above this unit cell, there is a one unit cell, so it's touching that as well. And there is one unit cell in the front of it as well, so it will be touching that atom which is in the front of it. So basically we have 1, 2, 3, and 4, and 5, and 1 in the front of that, which is 6. So basically there are 6 atoms touching this atom, and that's why we say the coordination number for the simple cubic crystal structure is 6 basically. And this is what we are saying, coordination number is equal to 6. Another way of looking at this, just to look at the lattice positions there, this is, we focus on one atom, so this is the atom we can focus on, and we can see in the lattice, as you can see, this is the unit cells are here, are shown, all of them. This is one, this is the other one which is here, okay, and this is the one at the back, and so all of them are shown. So basically this atom, how many atoms will it be touching? This is 1, and this is 2, and this is 3, and this is 4. You can see you can see that atom has 1 in the front of it, 1 and 1 in the back of it. You see, this is the 1. It has 1 in the front of back of it, and it will have 1 in the front of it as well. This is what we are showing here, right? So the same thing here. So I will select this because it will be having all the unit cells sharing it. So this is 1, 2, and 3, and 4, and 1 from the top and 1 from the bottom. So these are all the atoms which are touching it. The coordination number is basically 6. The simple cubic crystal structure we normally cover for illustration only because it helps out to understand the other ones. Why we don't focus on it? Because it's not actually common. It's rare, as I'm saying here. It's rare in metals due to poor packing. Yani normally, why it is rare? Because normally metals have good packing. So why it has good packing? Well, we have mentioned different reasons, and one of the reasons is that the atoms in the metals, no, in materials normally generally tend to go to the lowest energy level, and that's why they close on each other to that level, which gives us good packing. The only material that I know which displays the simple cubic crystal structure is the polonium, which we looked at in the previous lecture. Polonium. The atomic packing factor, which is the APF, is for a simple cubic crystal structure is 0.52. We are going to calculate that in a minute. Of course, coordination number is 6. We have already seen that. We talked about the close pack directions. What are the close pack directions in the cubic, in the simple cubic crystal structure? Are the you can see this is the simple cubic crystal structure now. Where are the atoms touching one another? This is where it is touching one another. Are they touching through the diagonal? No, there is a gap, as you could see there. So the direction where the atoms are touching one another is the cube edges actually. It's this direction, it's this direction, it's this direction. Any cube edge, you will find that the atoms are touching one another. So these directions are referred to as the close pack directions. The directions in the close pack directions in the simple cubic crystal structures are the cube edges, as I am showing there. Next, so we looked at materials which display this crystal structure, coordination number, and close pack direction. Next, we are going to calculate the APF. So what is the APF? The APF, the atomic packing factor, is basically the volume of the atoms in the unit cell divided by the volume of the unit cell. How much atom volume we have in this unit cell, that is the numerator. How much atom volume do we have in the unit cell divided by the volume of the unit cell. The volume of the unit cell is this times that. And we know that the lattice parameter, normally it is A. We name it as A, the lattice parameter. So basically the volume of the unit cell is equal to A times A times A. So that is A cubed, basically. So we are going to look at the equation in a minute. Let me go to the pen. And let me go to the color. Let's see, black. So let me erase this for a minute, and then we are going to bring it back again in order to simplify the thing for you right from the beginning. Let's suppose this is R. I'm going to put an R there. Okay, so that is R cubed. So basically, the volume of the unit cell, that is clear. It is A cubed, as I mentioned. It is A times A times A. That is clear. So this is A cubed, and simple. The volume of the atoms in the unit cell. How much volume of the atoms we have in the unit cell? It is the number of atoms that we have, right? How many atoms do we have? We have one. Number of atoms which are there is how many? It's 1, 2, 3, but these are 1/8 of an atom, right? This is 1/8 of an atom. Each one of them is 1/8 of an atom. So we have 8 1/8 of an atom, which will become, 8 times 1/8, which will become 1 atom per unit cell. So number of atom per unit cell, we could calculate it using this equation as well. We don't have internal atoms there, that's 0. We don't have phase atoms, that is 0. We have corner atoms, this is 8. We have 8 corner atoms. This is 1, 2, 3, 4, 5, 6, 7, and 1 at the back there. That is 8. So 8 times divided by 8, this gives us 1. The number of atoms per unit cell for the simple cubic crystal structure, we did it in the previous lectures as well. So that is basically 8. Now when we come to the calculation of the APF again, we say the volume of the atoms in the unit cell is equal to the number of unit cells times the volume of the sphere, of the volume of that atom. Volume is normally of a sphere is 4 over 3 pi r cubed, right? This is from your previous knowledge. So this is 4 over 3 pi r cubed times the number of atoms per unit cell gives you the volume of the atom in that unit cell. Now we have R and A here, where we find the relationship between R and A in order to cancel one of them. So basically, if we want to know the relationship between them, we look at just in the close back direction, we see that this is one R and this is a second R. So this is basically one R and this is two R's there. So you can say that A, the value of A, the lattice parameter, is equal to 2R. So A is equal to 2R, or you can say also A is equal to 2R, or you can say R is equal to 0.5A. So that relationship you can substitute into the R which you have here. So basically you can erase this, eraser, you can erase that, and instead of R cubed, you write 0.5A. Plug the number here. Once you do that, then you can cancel out the A cube or the A cube here, and you only have numbers there. You plug the number in your calculator, you will find that the atomic packing factor is equal to 0.52. And this is very low actually for the metals. The number is low, and that's why you have it. This gives poor packing actually for the material, and that's why it is rare. Any question? Any question, guys? All right. No question. We will go to the guys. You're with me, right?
الفوليوم of atoms على طول نفسه.
الفوليوم of the
atoms على طول نفسه ولا يتغير؟
يتغير طبعا. It depends on the number of atoms per unit cell. Here we have only one atom per unit cell, right? Okay. In the other crystal structures, we will see how many atoms we have in the unit cell. We will calculate that.
زي ده كان مثلا ثلاثة أرباع شيء، يعني مو شكل منتظم نعرفه.
بنشوف الحين in the body center cubic, in the face center cubic, we will see in the hexagonal close back it will be different. We will see that in a minute. So that depends on the number of atoms per unit cell. That volume of the unit cell, of course, that's a constant formula for all of them. But this is what differs. How many atoms you have per unit cell, the way we are calculating that will be different.
Doctor?
Yes.
So as the AFPF is greater, the packing will be better?
The packing will be better because you see, this is what you're looking at. It's the volume of the atoms in the unit cell divided by the volume of the unit cell. The maximum number this could get to is what? أكبر عدد ممكن يوصل لها الرقم كم؟
1.
Exactly, 1, right? So the less you have gaps there, the bigger, the closer the number to 1. Right? عادل شباب? Okay. Now let's go to the second type which we have talked about, which is the body center cubic crystal structure, and this is the abbreviation, the BCC crystal structure. In the BCC crystal structure, it's a bit different from the simple cubic crystal structure. In what? In that you have, it is cubic in the same way. So we have a cubic crystal structure again because we have different types, not only cubic actually there. We have many types. So this also, it is a cubic in the same way the simple cubic crystal structure are. So you have 8 corner atoms as you could see there. But in addition to that, we have one atom in the middle of the cube, as you could see there. This atom in the middle of the cube, it's called the internal atom, which we have there. This is what is different from the simple cubic crystal structure. These are the lattice positions of the atoms, which you can see, and this is the whole lattice. Yes.
دكتور هاي نفس النوع اللي غرق؟
You know?
BCC اف اي BCC او الليبرتي شيبس هاي نفس النوع دي؟
No, this is the BCC we are saying that. I'm gonna go like BCC crystal structure. It's a body center cubic crystal structure. The first one was the simple cubic crystal structure, which we have shown.
لا انا قاعد اسال عن في البدايه درسنا عن الحديد الليبرتي شيبس، قلت لنا اف اي BCC حديد كنا BCC structure مالك.
Yes, this is the one. Yes, this is what you meant. Yes. So this is the BCC crystal structure, as I said, and this is how it looks like. This is the lattice positions of the atoms, as we can see there. Now let us go and do the same things and calculate the important. Okay, let us see the different things that we have there. One important aspect that we want to look at is which materials display this type of crystal structure. Of course, we said the simple cubic crystal structure, there is only one metal, which is the polonium. Polonium only displays this type of crystal structure, but the body center cubic crystal structure, there are many materials which display this crystal structure, like the alpha iron, which we have. This is called the ferrite phase. We have the vanadium, the chromium, the molybdenum, the tungsten. You were asking about the Liberty ships. Yes, they were made from this alpha ferrite phase, alpha iron phase, which we have there. Notice that the BCC crystal structures, the atoms touch along the body diagonal. You can see where are the atoms touching. In the simple cubic crystal structure, they were touching in the, in the cube edges, at the cube edges, and this was the close pack direction basically. In here, there at the edges, there is a gap, as you could see there. So they are not touching one another. So therefore, this is not a close pack direction anymore. We said the importance of close pack direction in the previous lecture and explained that. Now, this is not a close pack direction. This is not a close pack direction, as you could see there. So basically, the close pack directions, the directions where the atoms touch one another, start from this corner, let's say, to that corner. If we make a line, you can see that the atoms are touching one another. This is touching here, and then this is the atom, and it's touching the atom here to the end of that corner. So basically, these are called, or the cube diagonals in the body center cubic crystal structure are the close pack directions. So let us look at again and look at the different things that we have. First of all, the APF for the body center cubic crystal structure is 0.68. We are going to calculate that in a minute, but as you could see, the number is higher than the simple cubic crystal structure, which was 0.52. We are going to calculate this in a minute down there. Before that, let us look at the coordination number. In order to calculate or determine the coordination number, we can just look at one atom, focus on it, and see how many atoms are touching it. The best and easiest way is to look at the internal atom, which we have here, that atom here in the middle. So how many atoms are touching this atom? Simply, you can see this is touching it from here, this is touching it, this is touching it, this is touching it. 4 from the top, 4 from the bottom, and basically 4 plus 4 is equal to 8. Coordination number will be 8. Very simple to visualize that. So these are the coordination numbers. The close pack directions are the cube diagonals, which I already explained in the previous page. All the cube diagonals are considered to be close pack directions from here to there and from here to the other corner, which we have there as well. Okay, so this is the close pack directions. Let me erase this in the same way we did in the previous one, and let me put that as R, the value of R there. So basically, in order to calculate the APF for the BCC crystal structure, it is the same formula: the volume of the atoms in the unit cell divided by the volume of the unit cell. The volume of the unit cell itself, it's A times A times A, which is A cubed, in the same way. But one notice I want to make is this A times A times A is the same as the simple cubic crystal structure A. Is the lattice parameter A here the same as the lattice parameter in the simple cubic crystal structure? No, it is not, of course. Why? Because as you could see, this is R for the material, and you have for the metal, for the atom, and this is a gap there. So obviously the A will be different than there as well. So this is one thing I just wanted you to know, because later on we will be using that information to know the solubility of the atoms of the alloying elements in the material. So we will be discussing that later. So the volume of the unit cell is A cubed. That is simple. We can do that. Now we say this is the number of atoms per unit cell times the volume of one atom. So what is the number of atoms per unit cell? We can simply determine that. Here we don't have any phase atoms there. But we have internal atoms from the formula which we are having here. This is N is equal to Ni plus Nf over 2 plus Nc over 8. Ni, it's the internal atoms. We have one internal atom. So basically the Ni will be 1. The Nf, we don't have any phase atoms, so this is 0. The N corners, it is in the same way as the simple cubic crystal structure, so this is basically 8. So you have 8 over 8. So this is 1 plus 8 over 8, which equals to basically 2. So the number of atoms per unit cell will be 2. So we can plug for the number of atoms per unit cell here as the number 2 times 4 over 3 pi R cubed divided by A cubed. Again, we want to find a relationship between the R and the A in order to cancel out one of them. What is the relationship that we can make out from there? Of course, here we don't, in the simple cubic, it was simple. A was equal to 2R. Here it is not, due to that gap that you could see there. In order to resolve the issue there, we can look at Pythagoras theorem. We can look at this length. What is this length equal to? This is 1R, this is 2R, this is 3R, and this is 4R. So basically that is equal basically to 4R, isn't it? This length is equal to, which is the hypotenuse of that triangle, it's equal to 4R. And from the Pythagoras theorem, you can say that this is A, again, right? This is A, and that length there, from here to there, if we name it as H, if you want, we can say this is H. So we can say that 4R, let me write it there, 4R square equals to what? Equals to 4R square is equal to A square plus H square. So equals to A square plus H square. Right? And if we know that also, if we know that H square from the other triangle, from this triangle, this H square is equal to A square plus A square, because this is also A. This is also A. So A square plus A square is equal to H square. So H square also equals to A square plus a square, which is equal to 2a square, صح? This equals to 2a square. So you can therefore say this is equal to 2a square. Therefore, 4r square is equal to a square plus, instead of h square we say here, we say it's equal to 2a square. We plug it in here. You put the 2a square instead of this. So a square plus 2a square is equal to 3a square. So that is basically what we have. Take the root of both sides of this side and this side. It gives you 4r is equal to square root of 3a. And that's the relationship that we are getting here. 4r is equal to square root of 3a. And if you plug that in this equation, instead of r, you put this here, you put it here, and now square root of 3a over 4 we have here. You can cancel out the a cube with the a cube. You have only numbers there. You plug the number in your calculator and you will get the 0.68 as the atomic packing factor. Clear, Shabab?
Doctor?
Yes.
Is it possible that we have more than one interior atom in the same unit cell?
Yes, we can have more than, but not for this one. هاي BCC الحين. this is how it behaves. هاي يتصرف بهالطريقة. ما ممكن إن نقول لك يتصرف بطريقة ثانية. This is the BCC crystal structure which looks like that. Of course, there are other crystal structures which we will see, not the next one, the other one. You will see that there are more than one internal atom there. Okay.
Okay.
So now this is for the body
دكتور.
center. Yes.
احنا قلنا دكتور انهم 4 ار لان عندنا 4 راديوس له.
ايوه. We have one. الكرسر لما اكتب واضح الصغير. This is 1R. This is 2R. صح؟ 3 and 4. So that's why I use that length in order to make the relationship. And because that is basically, why am I using it? That's the close back direction. The atoms are touching in this direction. Yes.
اوكي بس كنت متشوش الرقم من وين جاء 4.
Okay.
اوكي تمام.
All right. So we finished talking about the body center cubic crystal structure. We will now talk about the face center cubic crystal structure. The face F, center C, and cubic C. Again, FCC crystal structure, as we have mentioned. Now, by the way, you need to know, I need to mention that here. You need to know the full name of the crystal structure, and you need to know the abbreviations as well. The abbreviation, the short form as well. Or I can ask you what this short form is for. You need to say face center cubic crystal structure, and the same for the other crystal structures which we are going to deal with. The face center cubic crystal structure has a different look. It organizes itself differently. It is the same as the simple cubic crystal structure, and the body center cubic crystal structure also is that in the corner atoms. In the same way, you have 8 corner atoms, but in this one, it does not have any internal atoms inside, but it has a phase atom there. And as you can see, a phase atom, basically, when there is a phase atom, the phase atom is shared, the phase atom is shared by 2 atoms, basically, by 2 unit cells, by 2 unit cells. Half of it is in this unit cell, and the other half is in the neighboring unit cell, which is beside it. The same thing here. This atom, half of it is in this unit cell, and the other half at the top is in the other unit cell. So that's why in the formula, when we calculate the number of atoms per unit cell, as you can see here, we say NF over 2. Why do we say over 2? Because half of it is in the unit cell. Any phase atom, half of it is calculated to be in the unit cell. And the same way we did for the corner atoms, we said it's 1/8 of an atom, so that's why every corner atom, number of corner atom is divided by 8 due to that, because it's 1/8 of an atom there. So this is how the phase center cubic crystal structure arrange itself. This is the lattice positions of the atoms as it is shown in the phase of every in every phase of the cube. There is an atom in addition to the corner atoms, which 8 corner atoms, which you could see there. This is how the atoms look like there also, and another way to look at it. As you could see here, in the middle there, in the middle, which we cannot see there, in the middle here, there is a gap. So that's why the diagonal there is not a close back direction, because you have a gap there. Unlike the body center cubic, in the middle there was an internal atom, and close back directions were the cube diagonals. Here the cube diagonals are not close back directions. Also, the cube edges are not close back directions also here, because of that big gap which you could see due to the phase atoms which is placed there. So these are not close back directions, but the close back directions here are actually the phase diagonals here. That is a close back direction. This is one close back direction. You see the atoms are touching here and touching there. So this is a close back direction. And I'm showing it there as well. This is a close back direction in the FCC crystal structure. Actually, not only this, of course, it is all the phase diagonals will be, will be close back directions, as you can see there. All of them are close back there. All the phase diagonals are close back directions in the cube, which you can see there. Now, if we calculate, I don't want to do that here. I will do it on the next page. And this is the material with selected unit cell there. The typical metals which display this type of crystal structure are the gamma iron. You can see in the BCC, the alpha iron. Yeah, that's an example of a BCC crystal structure here. But examples of the FCC crystal structure, we have the gamma iron, which we refer to as the austenite phase. We have the aluminium, we have the nickel, copper, gold, silver, platinum, gold. They all display this type of crystal structure. Now, similar to what we have done in the previous crystal structures, we will do here as well. Compare the different things. The atomic packing factor, the APF, for the phase center cubic crystal structure is 0.74, which is the maximum packing factor possible for the atoms, and this is what I'm saying. So as you can see, for FCC is higher than the BCC, and it's higher than the simple cubic crystal structures. We will calculate that in a minute, which we are going to do down there. Coordination number, we can look at the coordination number of the crystal structure there. How do we do that? Well, basically we can select easiest atom and focus on that atom, and then see how many atoms are touching it. The simple atom to do that is this atom. For the bigger pointer in this case, since we need to do that. So this is the atom we are talking about. Let's see how many atoms are touching this atom. So, of course, these 4 atoms which you could see here, the corner atoms are clearly touching. This is very clear to see, صح? This is very clear to see. But from the bottom here, also this atom is touching that atom as well. The phase atoms are also touching that atom. And from that side also we have a phase atom touching it from here, and from this side there is a phase atom also touching that. So this is 4, and this also is another 4. But still, this is half of the atom. If we draw the rest of the atom, basically, the rest of the atom comes up there. This is the second half of the atom. So we have We have also, after the corner atoms, we have face atom here and a face atom here. So we have a face atom basically here, a face atom here, and on this side and on that side. So we have also face atoms touching the upper one, and the other level of the face atoms touching from here, and one from here, and one from here as well, touching as well. So this is 1, 2, 3, 4 also there. So basically, how many atoms will be touching that atoms then? That atom then? 4 and 4 and 4. 4 times 3, which becomes 36, صح? Which is 12, of course. Okay, 4 times 3 is 4. So that is 12 atoms. So the coordination number of the FCC crystal structure is basically 12. Yes.
مو في كورنر اتوم بعد في الجهة الثانية يلمسونه؟
This is what we are looking at. يعني once you have the you see انت قاعد تقول كورنر اتوم بعد. طيب وين هاي الاتوم قاعدين نتكلم عنه صح؟ صح؟ انزين تحت شنو فيس اتوم صح؟ الكورنر اتوم هذه بيكون بيوصل له هاي كورنر اتوم صح؟
لا الكورنر اتوم اللي فوق
حبيبي تشوف اللي تحت اول علشان ابين لك اللي فوق، لان الفوق مو مرسوم له. هاي الكورنر اتومز will it be touching this atom؟ لا انزين الحين ليش؟ لان بينهم شنو؟ فيس اتوم صح؟ انزين الحين كورنر اتوم بعدين فيس اتوم بيكون عندنا فوق، بيكون كورنر اتوم اللي فوق نفس ذلين. They will not be touching this atom صح ولا لا؟ Because we have a face atom there وبعدين الكورنر اتوم ذلين نفس ذي it will not be reaching that atom. بين صح ولا لا؟ فيس اتوم touching كورنر اتوم touching بعدين اذا عندك فيس اتوم نفس الطريقه اذا رحت تحت كورنر اتوم touching face atom touching بعدين corner atom wouldn't be touching that one but will be touching the atom which is below there صح؟
دكتور.
Okay, so basically we have 12. Coordination number is 12 basically for the FCC crystal structure. And close back directions we have already shown that it is phase diagonals in the previous slide. We have shown that the phase diagonals is equal to 12. Let us now finally find the number of atoms per unit cell and also find the atomic packing factor. This is the R. I'm doing the same thing for the other ones as well. So basically, let us calculate the number of atoms per unit cell. Here, the equation is somewhere, but I don't see it here. But anyways, the N, we will write it here. N is equal to Ni, sorry, at the beginning, Ni plus Nf over 2, which is Nf, waste of time, Nf over 2, equation not aligned, plus the Nc over 8. All right, so that is the Nc over 8. We can do the calculation the same way. Do we have any internal atoms? We don't have internal atoms. That was in the body center cubic crystal structure. How many Nf do we have? How many phase atoms do we have? We have 1, 2, 3, and 4 at this side, 5, and 6, right? So these are basically all شنو نسميهم phase atoms there. So you have 6 phase atoms. 6 divided by 2, and this is 8. Also 8 divided. So 6 divided by 2 is equal to 3. And 3 plus 1 is equal to 16, صح? Is equal to 4. So the number of atoms per unit cell is equal to 4. So in the atomic packing factor now, it's the number of atoms per unit cell times the volume of one atom divided by A cube in the same way. So the lattice, the volume of the unit cell is A times A times A. And again, this lattice parameter in the FCC crystal structure is different than the lattice parameter in the BCC crystal structure, is different from the lattice parameter in the simple cubic crystal structure. So this is equal to A cube. Number of atom per unit cell, we plug that number here, times 4 over 3 pi R cube. Now that R, we find the relationship between it and A in order to cancel out that number and get the atomic packing factor. Simply, you can look at that direction, which is the close pack direction basically, and you can say this is equal to how much? This is 1, 2, 3, 4 R's. So basically, this is equal to 4R. In this case, in the face intercubic, this is the one which is equal to 4R. And you can say 4R square is equal to A square plus A square. So you can say 4R square is equal to A square plus A square is equal to 2A square. صح? Is equal to 2A square. يعني A square plus A square. I'm not going to write that. A square plus A square is equal to 2A square. Take the root of both sides. This will become 4R, and this will become square root of 2A. And that's the relationship that we have here between the R and the A. 4R is equal to square root of 2A. The square removes that. So if you plug in that relationship, the value of R is equal to square root of 2 divided by 4A into the value of R here. There is that. So this is what you are going to have. And then if you come and cancel out the A cube there, you have only a number there. If you calculate that number, you will get the atomic packing factor to be 0.74. Any question? Any question? No questions. Next, in the hexagonal close pack crystal structure, yeah. Time is up. Okay, we will stop here today, and we will continue next time.
دكتور هو يقدر يطوف الوان الارض رقم؟
لا ما يقدر.
على شيء وان.
No, we have some students have already asked about this a few minutes back. They said that how much should the number be? Maximum number will be 1, because as we have seen in the formula,
يعني هو percentage.
It's the volume of the atoms in the unit cell. Volume of the atoms, how much volume you have in the atom, divided by the volume of the unit cell. Volume of the unit cell, it's A by A by A. That's the maximum that you could be having, صح? And volume of the atoms will be smaller than that normally. It cannot go to the same volume of the unit cell itself. So that number will be always less than 1. Maximum packing is actually 0.74. Since time has finished, I need to stop the recording for the other students to be able to watch the video in the time.